Okay, so today we're reviewing over a old concept from Algebra 2. Basically, this is whiteboards today with an opportunity for you guys to take notes here and there. So as you're going through, again, all this stuff's been from Algebra 2. So this is more of, okay, do you know how to do this? If so, that's good. But if not, there are notes there to help you. You probably want to add those examples to your notes so then that way you're unsure of it because this will be on your final. Okay, so the first one is you're going to sketch the graph of f of x equals 3x, 3 to the x plus 1. All right, so hold your whiteboards. What'd you get? Okay, now technically, you guys are all wrong, but that is the closest to the right answer because none of these are actually the correct answers up here on the board. The one that I copied and pasted from didn't have anyone as the correct answer. But C would have been the closest. Now, whatever I've always been telling you guys, when you don't know how to graph something, you can always default to what? Table. The table. A good old XY table, which means you can plug in values for X, and solve for Y. That's when you point on your curve. Your classic point is you can always plug in a 0. When you plug in 0 for X, this is review. 3 to the 0 power is 1. 3 to the 0 power is 1. Always, always, always. So 1 plus 1 is, so the point 0, 2 should have been on your curve, but none of these has 0, 2. But this one is the closest to this particular function. These are called what types? What types of functions are these? Exponential. And all exponential curves look basically how you see here. But the reason why this one is the closest is because an exponential graph always crosses through, before you moved it up, down, left, right, stretch, compressed it, whatever, always cross your y-axis at 0, 1. Okay? Today's topic that we're reviewing is exponentials and logarithmic functions, okay? The piece of paper is for any notes that you have forgotten about this concept. Okay, the whiteboard is for your practice problems, so you do need to have a piece of paper out just in case you run across something that you may forget, such as the difference between exponential growth and decay. Right here, b to the x is your standard makeup of an exponential function. Okay, if b is greater than 1, that means we have growth, which means that you're increasing. If b is in between 0 and 1, that means you're decreasing, hence decay. And if you notice, both of these graphs cross through the y-axis at 0, 1, and they both have what's their end behavior for decay? As x approaches positive infinity, y is approaching 0, which means there's a what at y equals 0? As an asymptote. There's actually an asymptote for both the exponential growth and decay. Okay? They share some similar properties too. Okay? What's the domain of this function? Or of either of these? Negative infinity to positive infinity. What's the range? 0 to infinity. Is 0 included? No, because there's an asymptote there. So they have those features. Honestly, the only thing that really differs between them is the fact that one's a growth, one's decay, which means their end behaviors are going to be different. Okay? So, the next example, or the next problem I want you to give a try, okay? Think about it. It's going to be dealing with the graphs. I want you to think about it, and I want you to answer. I'm going to give you 1 minute to do it, okay? So you got 1 minute to answer this question. You're putting A, B, C, or D. Yes, the answer for this one is B. The answer for this one is B. Even though we just went over, one thing you have to realize is that every exponential function is set up this way. So if you have a plus 1, think back to the beginning of the year. What's that plus 1 mean to the function? It means it moves up 1. Your transformations. So another way you could look at it was your horizontal asymptote, and actually it was this one. It's no longer at 0, it's now at 1. Or more specifically, y equals 1. Everything got moved up 1 unit. Okay? So you could have seen that it was definitely this one instead of the other two. You could have looked at the y-intercept by plugging in 0 for x, realizing that 3 to the 0 power is 1, adding 1 to get 2. The domains wouldn't distinguish anything, and neither was it increasing. Okay? So coming back to you, some of this stuff from Algebra 2. Yeah? Okay. So, we talked about this already, but here are the properties just laid out for you. Again, the domains are the same, negative infinity to infinity. The range, 0 to infinity, like you guys said. Both have a y-intercept of 1. They don't cross the x-axis, y, because there's an asymptote asymptote there, okay? They don't have any extrema. The only main difference between the two is their end behavior. As x approaches infinity for this one, y is approaching infinity, but as x is approaching negative infinity, it's approaching 0, and it's the opposite here, okay? We're good? I want you guys to try this one, okay? Give you about a minute. Let y'all remember. You'll need your calculator for this one. You will. What is that?
3 numbers.
We about to that you oh.
Something to the n power plus the number. Or am I thinking of the wrong one?
You might think of the wrong one. Because there's a few forms that have what you just said in the
It's like, well, it's sequence. And
Good
x to the n power plus something. I don't know what
You might think of sequence. Yeah, sequence. Alright, someone say anything like that answer? Or we stuck? Some stuff, there's gonna be some stuff that like I hit on this year too. That's one step. Oh, I did not pause this. All right, so. Hey, Nevin. Okay. Huh? All right. So for this particular problem, you do need a certain type of formula, okay? Because it's telling you that the bar does the same for their son's education, and they posited this much to start with, and they have an account that has 7.6% per year compounded continuously. This right here is key. There was a formula that dealt with continuous compounding that we did back in Algebra 2. Does anybody remember? Well, there would have been two formulas that we would have talked about around this time. They both deal with money. They were only used when we dealt with money. There was this formula. A equals P, parentheses 1 plus R over N, N to the T. This was used for compounded, continuous compounding, or not, compound interest, that's what it was. Where P represented your principal amount, aka your initial, how much you originally deposited. R was your rate, your interest rate, always as a decimal, okay? Your interest rate always gives you as percentage, so you want to convert it into a decimal. N represents the number of times it got compounded in a year, meaning it got compounded monthly, compounded quarterly, compounded semi-annually, compounded daily, like it actually says that in the problem. And then T represents the years. A represents the balance, the final amount after a certain number of years. This formula looks familiar though, right? Okay. Alright, there was another formula that was similar to this, but this the other formula basically dealt with continuous compounding. The difference between this one that's up here on the board now and the one I'm about to go to, this one that's on the board right now deals with you getting interest at a certain point in time during the year. Okay, that's what the N represents. That tells you the number of times that you're actually receiving your interest. Quarterly means 4. You're getting it 4 different points in the year. Daily means you're getting it every day. Compounding continuously meaning that it's not like somebody's going to log in and say, okay, here, let me apply your interest. It's happening all the time. Continuous compounding is this formula. A equals P, E raised to the RT. P is still your principal amount, still the amount you originally invest. R is still your rate, written as a decimal, and T is still your time in years for your final amount. E is the number 2.7178, whatever, is in your calculator. Okay, it does not represent a particular piece of the problem, it just represents that number. And you can find E by doing what? How can you find E on your calculator? Second. Okay, you can do the second button and then you can do the division button. Okay? If you do this, it just gives you an E, which means that you would have to type the caret button next, so then that way you can plug in the exponent. There's another way you can get the E. Second ln. Second ln basically takes you straight to E with the exponent already. Okay? So, but they still have the same E. Okay? So this one's used again for compounding continuous compounding. Okay? So now let's go back to that problem. And let's work this out. Okay? You got the formulas now, so let's work them out now. The answer is C. Keywords, continuous compound, that's why I was harping on it. Continuous compounding is the formula A equals P e to the RT. What's R? Very good. You got to convert it into a decimal and then you multiply by your time, which is 9. And that's how you get C. Okay? These are only used with money. Okay? Here's another one. Do this one. 45 seconds. Our answer is C. Yes. A equals 1500 e to the 0.04 times 8. Yes, neither of these were dealing with compounding compound interest, but if they did ask you again, let's just review compound interest. If it asked you to compound quarterly, what number is that? 4. Monthly, 12. Daily, because we do not consider leap years. What about semi-annually? 2. And what about weekly? 52. There are 52 weeks in a year for those who didn't know. Okay? Now, these other two formulas, very similar to the ones that I just showed you that dealt with money. These deal with everything else that's not money. Population growth, bacteria, a population of an animal, a critter, whatever. Okay, it's the same setup if you notice. Okay, this is the same setup as A equals P1 plus R over N into the T. The only difference is you don't compound population and people and animals, you know, a certain point in time in the year. Usually it's only done annually when you look at a population or you look at a species or something like that, okay? So that's why there is no N for this problem. N in the sense of like being compounded, okay? But this capital N represents that final amount. That N sub 0, which represents initial, okay, that's your initial amount that you start with. R represents your rate, still as a decimal, okay? If R is greater than 0, then you know you're going to be dealing with the growth, and you add it to 1, okay? But if it's a decay, then inside that parentheses, you're going to have 1 minus R instead. So there's decay is 1 minus, all right? T is still your years. When you have continuous exponential growth, this really is the formula A equals PE to the RT, except N represents your final amount, N naught, that N sub 0 represents your initial, and instead of R, you have K, which just basically still means your rate, okay? But it's distinguished the two, all right? So they're pretty much used the same way. It's just this time, these formulas are used for everything else but money, okay? You guys understand that? So on your whiteboard, I want you guys to try this problem right here, this population problem. The answer is A. The answer is A. Because it is increasing at a rate of 2% annually, that basically, is that going to be regular exponential growth or continuous? It's regular. That annually kind of is like what that compounding, quarterly compounded, semi-annually would be, that kind of correlation. So in here, you're going to plug in 15 to 60. You're going to do 1 plus your rate. What's your rate? 0.02 raised to the 10 to get your 10 years, and then you trade out for 20 to get your 20 years, and the answer is A. Okay? Coming back to you from exponential functions, keep asking. I just want to make sure it's clicking. Is anything else associated with exponential functions clicking? Like maybe some stuff that you haven't gone over yet, but it's coming back to you?
I don't understand how you
Like basically, this right here, this word right here, basically tells you is that every year they're checking the population, which means it's not a continuous thing that is increasing at 2%. That means that every year they're taking the population of the town and then they're looking at it compared to the other years and realizing that okay, the rate is 2% in which this is increasing. Continuous basically means that they took a population to start with and they're just letting it go. And at no point in time are they ever checking in to see, hey, anybody have a baby this year? Let's see, type thing, okay? And it's also not saying, hey, come on, baby, type thing. Okay, that would be continuous growth, okay? Got me? All right. All right, look familiar? All right, well, think about this one almost.